Okay, so the packet begins with us talking about angle measurements. So in particular, we want to talk about radians and degrees. And when it comes to degrees, decimal form or degrees, minutes, and seconds. Now, the way you convert to radian measure, if you have a degree, is you're going to multiply your degree measure, whatever it is, by pi over 180. That's the way you're going to convert to radian measure. So for example, 10 degrees, you're going to say 10 times pi over 180. Okay? And then, of course, that'd be pi over 18. You simplify it. Same for this negative. Negative 14 times pi over 180. There, like that. Now, if you want to convert to degrees and you're given radians, and you know you have radians because you don't have the little circle. I don't have pi over 5 and little 0 up there like I do here. What you're going to do is you're going to multiply your radians by 180 over pi. Okay, so I'm going to multiply by 180 over pi. So pi over 5 times 180 over pi. And then, of course, you can simplify that. 1/10 is 1/10 times 180 over pi. And you can simplify that as well. So this would be like 18 over pi here. And notice, sometimes it throws people that there's 1/10 instead of, there's no pi in there. It's not like pi over 10. Well, that's okay. Radians don't have to have a pi symbol in them. So now let's go on down here where it says convert to decimal form from degrees, minutes, and seconds. So let's look at that one. When you see 10 degrees, 2 minutes, and 4 seconds, here's what that means. That means 10 degrees, and then a fraction of another degree, that's 12/60ths of a degree, and then a fraction more, 20/3600ths of a degree. In other words, it's base 60. So it's the minutes over 60 to the first power plus the seconds over 60 to the second power. And that's the way you do both of these. This negative, you would have -8. Let's do this. Let's put it all in parentheses. Plus 12 over 60 plus 20 over 3600. Now, notice I put the whole thing in parentheses. Okay? You don't want to just put the -8 and then plus 12/60ths plus 20/3600ths. You put the whole of it in parentheses. That's important. And then you would just work that out. Now, if you're going the other way, if you've got decimals and you want to go to degrees, minutes, and seconds, let's see what that would be. Now, notice this first one. You've got 10 degrees and then half of another degree. Well, if you're talking about a degree being divided into 60 equal minutes, this would be 10 degrees and half of another, which is half of 60. Okay, half of 60 minutes. So that would be 30 minutes. So this would be 10 degrees and 30 minutes. Now, that's the way we proceed with the degrees, minutes, and seconds if we're converting from decimals to degrees. Okay, so this next one, we've got -4 degrees, and then we multiply 0.25 times 60 minutes. See, we're taking 25% of another degree, which is 25% of 60 minutes, and that's going to be 15. So this one would be -4 degrees and 15 minutes. Okay, now this next one, let's look at this. We have 8 full degrees and then 0.126 of 60. Now, if we multiply that, 0.126 of 60, we get 7.56 minutes. So we have this. We have 8 full degrees, 7 full minutes, and then 0.56 of that 56% of another minute, which is um, 60, 60 seconds. Okay, so it's 0.56 of 60, and we get 33.6. And I'll just keep that as 33. That's accurate enough. So we have 8 degrees, 7 minutes, and 33 seconds. See, but every time, notice you multiply by 60. It's always you're saying, okay, the fraction of 60 minutes and then the fraction of 60 seconds. That's the way we do all of it. Okay, next we want to find the 6 trig functions for various angles. Now, I picked angles that are on the unit circle. Now, remember, the angles that are on the unit circle look like this. You've got angles that are like pi over 6, pi over 4, and pi over 3. In other words, you've got a 6 in the denominator, 4 in the denominator, or 3 in the denominator. And they're associated with these ordered pairs. Pi over 6 is associated with square root of 3 over 2, 1/2 here. Pi over 4, square root of 2 over 2, square root of 2 over 2. And pi over 3 is 1/2 comma square root of 3 over 2. And remember, the cosine is the x and the sine is the y. So if you're talking about pi over 6, so we've got sine alpha for pi over 6, that's going to be 1/2. See, the y coordinate. And we might as well go ahead and get cosecant, which is the reciprocal. Okay. Then we've got cosine, which is square root of 3 over 2. Secant is its reciprocal. And then we've got tangent, which is sine over cosine, which is 1 over the square root of 3. Its reciprocal is cotangent, which is square root of 3. Okay, so there's the first one. That's A. Now, B, you're not going to find 23 pi over 3 on the unit circle. But so you have to figure out, now you know right away the ordered pair that's associated with this is going to be 1/2 uh, square root of 3 over 2. Okay, because it's got a 3 in the bottom. The problem is you don't know what what's positive and what's negative. So we have to sketch this graph. Now remember, what I showed you was divide the denominator into the numerator. Now 3 will go into 23, 7 times. It goes in there 7 times, and then there is a remainder of 2. So let's look at this. We go 1, 2, 3, 4, 5, 6, 7. There's 7 half turns, and then 2/3 of the way around again. So 2/3 of the way around is going to put you in quadrant 4. And that means in quadrant 4, the x is positive and the y is negative. So there you can see the sine, the cosine, and then you go from there. Likewise, for C, you would do the same thing. You would say, okay, 4 will go into 9. See, here is 4 pi over 4 right there. Here is 8 pi over 4. And then you go 1 more fourth. Okay, so 4 pi over 4 is a half turn, 8 pi over 4, that's 2, and then 1 more. 4 will go into 9 2 times with a remainder of 1. So you would choose this ordered pair, sine, cosine, and so forth. Now we get to the inverse trig functions. Now, we were primarily working with sine, cosine, and tangent. They're inverses. Now remember that when we talk about sine, let's think about sine. Sine or inverse sine, let's say. Okay. Inverse sine is only going to output values in quadrant 1 and quadrant 2. In other words, it's only, and in particular, it's going to output values between negative pi over 2 and pi over 2, inclusive. So if you evaluate, if you do this, if you say, I want the sine, inverse sine of 1/2, well, it's going to give you pi over 6. That's that's the output for inverse sine. Now, there are other places on the unit circle where the sine is equal to 1/2. For example, 5 pi over 6. Sine of 5 pi over 6 is also 1/2. However, we have to limit ourselves to values between negative pi over 2 and pi over 2. Now, so remember, what we're saying is, we're saying, okay, what angle gives you a sine of that value? The answer is pi over 6. Now, cosine, on the other hand, is going to be in quadrants 1 and quadrants 2. So inverse cosine, that's going to give you value. You're going to get outputs between 0 and pi. Oh, I should use it could give you a 0 and pi. That's the output for cosine. So if we have cosine of inverse cosine of 1/2, that's going to be pi over 3. Even though 5 pi over 3 is also, the cosine of 5 pi over 3 is also 1/2. You have to limit your output to those values in the case of inverse cosine between 0 and pi. Now, as far as tangent goes, inverse tangent, well, it's a lot like sine. You're going to go between negative pi over 2 and pi over 2, but not inclusive. You won't include it. You want to include those endpoints. So if you look at this first one, arc sine of 1/2, well, we already said that is pi over 6. Arc cosine of negative 1/2, negative 1/2. Well, that's in quadrant 2, and that is going to be 2 pi over 3. 2 pi over 3. That's where cosine is negative 1/2. Now, arc tangent. Now we have 1 over the square root of 3. That means, you divide it sine by cosine. So you had 1/2 divided by square root of 3 over 2. You end up with the square root of 3 on the bottom. That means the sine was the 1/2 and the cosine was the square root of 3 over 2. That's the way you can think about it. Now, it's negative. That means you're going to be in quadrant 4. So let's think about where this happens. First of all, where is sine equal to 1/2 and cosine square root of 3 over 2? Well, at pi over 6. But we're in the fourth quadrant. We're between negative pi over 2 and pi over 2. So this is going to be negative pi over 6. Yeah, that's the way we have to look at that. That's the output. Now there's, arc tangent will also, you also have at 5 pi over 6, but that's outside the range, the output of arctan. Okay, now let's look at this next one. This says the sine of the angle that has the arctan of that has a tangent of 2/3. So you have to realize this right here is an angle, and this is just saying, well, what is the sine of that angle? Well, the fact that it has arctan of 2/3, that tells you something about the angle. Let's suppose this is the angle. That says that the opposite side is 2 and the adjacent side is 3. See, they're being more specific rather than just say sine of theta. They say the sine of theta where the opposite over the hypotenuse is 2/3. So then we can say, okay, this up here is 9 minus 4, square root of 5. So the sine of that would be opposite over hypotenuse. So we have to just work it out that way. Okay, so that's how we deal with these inverse trig functions. And the important thing is to remember the output interval. Now, this next one, I'm just asking you to use the inverse trig functions to find all the angles. So let's think about how this would work. If you have sine of theta equals some positive number, let's say a is a positive number, you could do this. You could say theta equals inverse sine of a. And you would find what you were looking for, and it would be in quadrant 1. So here is theta right here. You found that. And theta is inverse sine of a. But you know there's another angle that also has the uh, sine of theta equals a. In other words, there's another angle over here whose sine is also a. Now, if you think about it, this angle here is going to be the same as that one. So we need to figure out what that other angle is. Well, it's going to be pi minus theta. Pi minus theta. Yeah, that's what that other angle would be. Because look at this. Let's suppose that we have the sine of theta equals 1/2. So theta equals the inverse sine of 1/2, which is 30 degrees. Okay. Now, that's in quadrant 1. If I want the angle in quadrant 2, I'm going to do 180 minus 30 degrees. And then I get 150 degrees. So there are two angles. The inverse sine is only going to give you the one. It's going to give you 30 degrees. You have to find the 150. So you have to subtract. You have to say pi minus the angle that you just found, or 180 minus the angle you just found. Now let's look at cosine. And before we look at cosine, though, it doesn't matter if a is positive or not. If a were negative, let's suppose that we have the sine of theta equals a, and let's just say as a is negative. Now, when we do the inverse sine, when we do this, when we do that inverse sine, what we're going to get is we're going to get an angle down here, like this. And it's going to be a negative number, like negative pi over 6. Let's try this. Just put some concrete numbers with it. Let's suppose that we have this. Let's suppose that we have sine of theta is equal to negative 1/2. Well, if we do inverse sine of that, we're going to get negative 30 degrees. Negative 30 degrees. But that's not the only angle that when we take the sine of it, we get negative 1/2. There is another angle on one time around when we take one trip around the circle. So let's figure out what that. We know it's going to be in quadrant 4. So let's see how we would find that. Here's quadrant 4 over here, and there's the angle we're looking for. We're looking for this angle right here. So think about it. What if we just did like we did before? Take 180 minus the angle we just got. Okay. So then we've got like 210. So it still works. In other words, what we need to do is we need to say, okay, theta is equal to inverse sine of A, and also theta is equal to pi minus inverse sine of A. Yeah, works, even if A happens to be negative. Now let's look at cosine, and we'll look at the case where cosine is positive. So let's suppose we've got cosine theta is equal to A. Then theta is equal to inverse cosine of A. And that is right here in quadrant 1. Now, we also need to find this angle down here because uh, cosine is also positive in quadrant 4. So let's think how that would be. We could take 2 pi minus theta. Yeah, that would work. So let's think about this. Let's suppose that cosine of 1/2, or let's do this. Let's do cosine of theta equals 1/2. Well, theta is equal to inverse cosine of 1/2, which gives us 60 degrees. Now there's another angle in quadrant 4. The cosine of that angle is also 1/2. So what would we do? Well, we would take 360 minus 60, and we would get 300. And the cosine of 300 is also 1/2. So notice what we do. We get the inverse cosine. So theta is equal to inverse cosine of A. And theta is also equal to, well, 2 pi minus inverse cosine of A. Those are the two. Now, as far as tangent goes, let's take a look at tangent. Okay, so here we go. Let's suppose tangent theta is equal to A. Let's suppose A is positive, and it really doesn't matter. I'm just using positive, but it will generalize even if A is negative. And let's suppose that tangent is equal to, well, theta is equal to inverse tangent of A. That's going to give us an angle down here. Okay. Now, if theta happens to be positive, we also know there's another angle over here in this quadrant. So for example, let's suppose that we have tangent of theta is equal to 1 over the square root of 3. Let's just suppose that happens. Or let's do this. Let's, yeah, 1 over the square root of 3. Then that means that theta is equal to inverse tangent of 1 over the square root of 3, which is 30 degrees. Now there's another angle in quadrant 3 where the tangent is also, the tangent of that angle is also 1 over the square root of 3. That's going to be, so think about it. We need this angle right here to go around like this over here. Well, that's going to be, theta is going to equal 180 plus 30 in this case, right? Because these angles match up. So generally speaking, what we're going to have is that theta is going to equal inverse tangent of A. And theta is also going to equal inverse tangent of A plus 180. Okay, those two. So we've got for cosine, well, for sine, we've got theta equals inverse sine or 180 minus. For tangent, it's inverse tangent or 180 plus. And then for cotangent, for cosine, it's inverse cosine and then 360 minus inverse cosine. Anyway, so I've belabored this enough. I'm going to move on to the next section. So you can see how to work through that. Okay, now, if we want to find all the solutions, just in general, all the solutions to a trigonometric equation, if you have values on the unit circle. So you can just use the unit circle. So this set of problems here, I'm just asking, find all the solutions. You don't need to use inverse trig. I'm not requiring that. And the easiest way to do this, like for example, this first one is just say, well, x is equal to pi over 6 plus 2k pi, where k is an integer. Or where else? 5 pi over 6, where k is an element of the integers. Yeah. So all you're doing is looking on the unit circle and saying which angle will give me a y coordinate of 1/2. That's all. Now for cosine, here's what you get. Now we're going to get 2x. Okay. The cosine of something equaling 1/2. Well, that occurs at pi over 3 plus 2k pi. Also, 2x is equal to, let's see here, 5 pi over 3. And I just get that straight off the unit circle because we've got quadrant 1 and we've got quadrant 4. Okay, 5 pi over 3 it's in quadrant 4. You know that because 6 pi over 3, just one more up would be 2 pi. Now, I I want to solve for x, and what I've done here is I've solved for 2x, so I divide by 2. So pi over 6 plus k pi. 5 pi over 6 plus k pi. There are my solutions right there. Okay, now let's look at tangent. We've got uh, tangent 4x equals 1 over the square root of 3. Okay, now that happens at pi over 6. Okay, that's one place it happens. It also happens in quadrant 3. In other words, 4x is equal to 7 pi over 6. Okay, so it happens in quadrant 1 and quadrant 3. Because in quadrant 3, the sine and the cosine are the same signs. But dig this now. I could combine these. In other words, remember the period of tangent is pi. So I could just write this way. I could say, well, 4x is equal to pi over 6 plus k pi. I could combine them that way. See? Because, they're only 30 or 180 degrees apart, pi radians. Then I could divide by 4. Yeah, like that. So however you want to do it, you could just say x equals pi over 24 plus, k pi over 2, and then do the other one, 7 pi over 24 plus k pi over 2. But okay, now let's look at this next one. 2 sine squared x minus 1. Okay, first of all, solve for the trig function. Square root it. Yeah, there it goes. Now, of course, we're used to seeing this as the square root of 2 over 2, like that. Well, that's going to be all the multiples of pi over 4. So immediately you can just do this. You can say, okay, x is equal to pi over 4 plus k pi, or 2k pi. Getting ahead of myself. X equals 3 pi over 4 plus 2k pi. X is equal to 5 pi over 4 plus 2k pi. Or x is equal to 7 pi over 4 plus 2k pi. There. That is an expression of all the solutions. Now you can combine these. You could say, well, x is equal to pi over 4 plus k pi. And that takes care of these two. See, pi over 4 plus 4 pi over 4, or pi, would give you 5 pi over 4. And then you can combine these two. Okay. So that's an example of solving, solving those equations, finding all the solutions. Now, we want to talk about sketching graphs. And remember, the sketch of sine goes like this. The sketch of cosine goes like this. Those are the basic shapes. Now, I've got the first one here, 2 sine 3 x minus 1 plus 5. Now, what I had recommended is making a little box or a little rectangle, and down the middle putting a line of oscillation. And for this one, you've got 5. I take that 5 and put it right there, and then I add 2, add the amplitude, and I subtract the amplitude. Whoops. So I add and subtract the amplitude, and then I just put the graph, I just sketch it. So here we go. This is sine, so it looks something like this. Okay. Yeah. Now, you need to be able to know, okay, where does this graph start? Well, the inside starts to kick in here. This is the horizontal shifts. The graph is compressed. Everything is divided by 3 and shifted over to the right 1 unit. So, for example, this graph normally goes to 2 pi. It starts at 0 and goes to 2 pi, but now it's starting at 1 and going to 2 pi divided by b and add c. And notice the period is 2 pi divided by 3. And notice that if you start at 1 and add 2 pi over 3 to it, you get it to the end. So you can see here clearly how the period is involved there. So you want to have the starting and the stopping place for each one of those. Now, you also have the cosine, and the cosine, let me just write it over here. Okay, we have the line in here, the cosine. It's a right side up cosine. We've got -1. Whoops, write that better. We've got -1, -1. We add 3 to it and we get 2. We subtract 3 and we get -4. The graph starts at 2 and goes over here to 2 pi divided by 4 plus 2. Now I'll just real quickly put in the sign here. We've got an upside down sign. Okay, that's the key here. It starts here at 3, you add 5 and you get 8, you subtract 5 and you get -2. Okay. The graph starts at -2 and goes to 2 pi over pi plus 2. I mean, minus 2. Okay. So there are those sketches. Okay, now, if we want to go the other way, so instead of sketching a graph, we want to take the graph and write an equation. So I'm recommending that, well, on a lot of occasions, it's going to be good to use cosine. Okay, so I'm going to use that model. Now, I start off with getting the vertical. So you take the y max plus the y min and divide by 2. In this case, the y min looks like it's negative, well, -1 if you look at the scale here, -1 plus 3 divided by 2, so it looks like that's 1. Okay, and then A is going to be the y max minus D. So it looks like it's going to be 3 minus 1 is 2. Okay. For B, I'm going to count since this is going from 0 to 2 pi, I'm just going to count the humps here. It looks like I've got 1, 2, 3. Looks like it's going to be 3. Okay. And then C is going to equal where a max occurs. It looks like a max occurs here at 2. See, it looks like that. So there's my model. Y equals A is 2 cosine 3 x minus 2 plus 1. Yeah. Okay, so the next one, you've got, let's do a different color here. You've got D is equal to, let's see here, -2 plus 4 divided by 2, that's 1. You've got A. Now, notice, looks like, okay, there's what it's oscillating about. And then from there, it looks like we go up 2. See, go 1 and 2. Actually, we go up 3. I'm sorry, 3. Which, remember, I said is 4 minus 1. Okay, so from here to the top is 3. From here to the bottom is 3 as well. So we got A equals 3. We've got B is equal to 2 because I'm counting 2 of these high points. And then C is where the max occurs. It looks like the max occurs at 1. So Y equals 3 cosine of 2x minus 1 and plus 1. There it goes. Now, the next part, we have this application where we have a tidal. We're looking at the depth of water over time. And we're told that the max depth of the water occurs at 3 a.m. and it's 20 feet. The min occurs at 6 a.m. and it's 16 feet. Okay. And we want to come up with a model for this. Now, so we can start working through this. We know the line of oscillation is going to be the average between the min and the max. So that's 36 divided by 2, which would be 18. Okay, so that's the average. And then we need to know, well, what is A then? Well, A is going to be the max, which is 20, minus A, which is 2. Okay. We also need to know B. Now remember B, the period, we can always calculate the period by 2 pi divided by B. Likewise, B is equal to 2 pi divided by the period. So the period here, notice we go from 3 to 6, we go from high tide to low tide. Now that's half of a period because we got to get back to the high tide. So 3, 4, 5, that's 6 hours. for the complete cycle. So we get 2 pi divided by 6, which is pi over 3. Now C is where the high tide occurs, and the high tide occurs at 3. So we get a model that looks like this. We've got A, which is 2 cosine of pi over 3. And I'll use t since we're dealing with time. T minus 3 plus 18. There's that. Okay, now we want to look at the application, solving triangles. Now, first of all, for right triangles, we can just use the inverse sine, cosine, tangent and solve them that way. So this first one is a right triangle. Now you know that because 3 squared plus 4 squared equals 5 squared. But let's suppose you don't know that. You can try to use, so there are two things. We've got the law of sines. Let's look at this, law of sines. Okay, law of sines says cosine alpha over A equals cosine beta over B equals cosine gamma over C. And you can flip those as well. Then we've got law of cosines. And you got C squared equals A squared plus B squared. Now, that looks like Pythagorean theorem. But look, it's a little bit different. So we minus 2AB cosine gamma. Now, if you're dealing with a right triangle, and C is the side opposite the 90-degree angle, notice cosine of 90 degrees, that's just 0, and all you get is C squared equals A squared plus B squared. So you can try to use the law of cosines and see, in this one you could plug in and see that it's going to be the same as the Pythagorean theorem. But anyway, you look for where if A squared plus B squared equals C squared, then you've got a right triangle and you just use your trig functions. So for example, this one, we've got, let's see here, we've got 3, 4, and 5, let's say. Okay, and I'll say, this is A, this is B, and this is C. So we want to find angle alpha. Well, we can do this. We can do inverse tangent of 3 over 4. That's alpha. For, let's say this is beta, we can do inverse tangent of 4 over 3. And that's beta. And of course, we know the 90-degree angle there. But anyway, you can use the inverse trig functions and the trig functions just for right triangles. Now, for these others, what we want to do is, and notice this down here, you could also rewrite this so that you have it set up where you can solve for the angle. Okay, so like that. You could set it up that way. So, but let's look at this one here. Okay, for B. It looks like what we want to do is we've got A, which is 5, and we've got B, which is 6, and then there's an angle between them. Okay, so 105 degrees. And what we want to do is we want to find the rest of it. In other words, I want to find this over here, first of all. Well, the way we could find that is we have x squared is equal to 5 squared plus 6 squared. Notice you're just saying, okay, if I want to find a side, I take the sum of the squares of the other two sides minus 2 times those sides, cosine of the angle opposite. Okay, cosine of the angle opposite. Now, then we'll have this side. Okay, then you can go and you can use the law of sines to find these other two angles here. Okay, you can use the law of sines. So for example, if I want to know, okay, well, what about this angle here? I'll call this angle alpha. Okay, if I want to use, actually, I think I was calling, I guess this would be the way I'd set it up. This would be angle alpha over here. So if I wanted to solve for angle alpha, I could go sine alpha over 5 equals sine 105 over x, like that. Okay, let's take a look at this next one where we have a equals 5, alpha equals 10 degrees, and then b equals 13. Let me just erase some of this, give us some room here. Okay, now you don't have to sketch these out, but let's just see what this possibly could look like. We've got this angle here. Here's 10 degrees, that's A. This is 13. And then you've got 5 right here. So this is B, and this is A equals 5. And down here you've got beta. So that's kind of what the angle, the triangle might look like. Then you have that angle up there, gamma. Now notice there's some ambiguity here because I drew the 5 down this way. I could have made it cut back this way and got an alternative triangle. So there's a possibility that there's two triangles that we're going to have to find. Now remember, I said you can determine if there's going to be two triangles if you say B sine alpha is less than A is less than B. If that happens, then you can conclude, okay, there's going to be two solutions, and you realize, okay, I'm going to have a little bit of extra work to do. Now, if you calculate that, you would get 13 sine 10 degrees, and that equals about 2.2, which is indeed less than A, and that's less than B. So you know there's going to be two solutions. There's just no getting away from that. But you don't care at the moment. You're just going to go through here and try to solve this. Now, what we've got, so we just have to figure out what we want to solve first. Now, notice I've got sine beta over 13 is equal to sine 10 degrees over 5. That's the law of sines. See, I just try to use what I've been given there. Okay, so I've been given the angle 10 degrees and its opposite side, and what I'm trying to do is find the angle of a side, opposite a side that I was given. So this is perfect. So what I have then, what I can do is I can say, okay, sine beta is equal to 13 sine 10 degrees over 5. Now, if you calculate that, if you do 13 sine 10 divided by 5, and don't forget to close your parentheses, you get about 0.45148, something like that. And then I do inverse sine of that. Okay, so I do an inverse sine of that, and you get about 26.839 degrees. Okay. Now I know what beta is. Now I can find gamma because gamma is just going to equal 180 minus 10 degrees plus the 26.839. Okay. So if I do that, I do 180 minus 10 minus 26.839. I get 143.161 degrees. Now, those degrees should add up to 180. So if they don't, there's something, you made a calculation error somewhere. Now, the only thing I have left to do is find side C. So I've got C over sine of gamma equals A over sine of alpha, law of sines. Now, remember, so here's what we've got. We've got C over sine of 143.161 equals A, which is 5 over sine 10. So I can immediately, I got C is equal to 5 sine 143.161 degrees over sine of 10 degrees. Yeah. So if you calculate all that out, 5 times sine 143.161. Don't forget to close your parentheses around that trig function. Divide it by sine of 10. You get 17.263 approximately. Okay, now we've got alpha, beta, gamma, and we've got ABC. But remember, there are two solutions. So here's what we've got to do. We were given the side B, but we weren't given the angle B, the angle beta. That's our starting point. We have to go to the angle opposite the side that we were given. And we do it this way. So to get our new beta, I'll call it beta prime, is going to be 180 minus the old beta. Now, once you do that, here's what you'll have. You'll have alpha, you'll have A, you'll have B, and you'll have the new beta. And you just go through this process and you can find the new gamma and the new C. But for time's sake, I'll just leave it there. Okay, now let's move along. Okay, now we jump into the vectors. Now remember, when we talk about dot product, here's what we have. We just multiply corresponding components. 5 plus 12 plus 56. Okay, we just 1 times 5 plus 4 times 3 plus 8 times 7, and we get 73. Okay, we work that out, 73. Now we talk about the magnitude, the length of the vector. So the magnitude of V is going to be the square root of 1 squared plus 4 squared plus 7 squared. Okay, so that's going to be our magnitude of V, and that equals the square root of 66. Then the magnitude of W, same thing, the square root of 5 squared plus 3 squared plus 8 squared will give you the square root of 98. Okay, there those are. Now, the angle, remember the angle. So when we talk about if we talk about the angle between two vectors, remember we've got a formula for that. The cosine of the angle is equal to the dot product. So this would be, in this case, V dot W over the product of the magnitudes. Okay, so that's the formula for the angle between two vectors. So in our case here, this is going to, and then you can do inverse cosine. So we would have, we found the dot product to be 73, and then you've got the square root of 66 times the square root of 98. Yeah, that's how you would do that. So now, now on this one, I've got a mistake here. I said the angle. Okay, this right here is just the projection. So I need to take that out. the angle between projection. No, the projection. Now, remember the projection is just going to be this. We're going to take up top, we got V dot W, and down here the magnitude of V squared times V. Okay, so in this case, that's going to be 73 over uh, 66, and then 147. That would be the projection. Okay, next is the cross product. So we want V cross W. So, here's what I want to do. I want to do V cross W. Now, unlike the dot product, V cross W is going to give you a vector. In particular, it's going to give you a vector that's perpendicular to the V and the W. So let's see how this works. We've got I, J, K. We've got 1, 4, 7, and 5, 3, 8. Now it's very important, the order matters. So V cross W is going to give you the opposite of W cross V. So you need to keep that in mind. So here we go. So remember what we do first, we're going to take out this row and this column, and I'm going to say 4 times 8 minus 7 times 3. Okay. Then we take out this row, this column and this row, and we're going to go the opposite way. 7 times 5 minus 8 times 1. So we go the opposite on that one. Then we take out this column, this row, and we go 1 times 3 minus 4 times 5. And there's our projection. And if we dot product that by by V or W, we're going to get 0. Okay. And that's the cross product. Now, when it says find a unit vector in the direction of V, what you do is you simply divide, you take V. So this, in this case here, we've got V, which is 147, and we divide by its magnitude. So 1 over the square root of 66. And that will give you a unit vector, but in the same direction of V. Okay, now this next one, it says find the parametric form of a line that is parallel to the vector V and passes through -5, 4, and 7. Now, remember how this goes. If we have a vector, okay, so we have a vector parallel. So here we go. We've got V is equal to 1, 4, 7, and we've got a point, which is -5, 4, and 7. Okay, so it's going to go like this. You're going to have X is equal to T minus 5. See, the vector. T times the components of the vector. Y equals 4T plus 4. Okay, and then Z is equal to 7T plus 7. Now that was I regret having so many numbers similar. So look, let's just look at this. If we have a vector, A, B, C, and we have a point, X naught, Y naught, Z naught, we get X is equal to AT plus X naught, Y is equal to BT plus B naught, Y naught, and then Z is equal to CT plus C naught. Yeah, there it goes. That's how that works. That's the form of a line that we're looking for, just to be clear, because I had so many numbers the same. Now, what we want to do now, if we're given an equation, if we're given a set of parametric equations for a line and then another line, and we want to know, do those lines intersect? And if they do, what is the point of intersection? So let's see how we would tackle that. I'm giving myself some room here. Okay, clear this off. Okay, so here we go. In other words, we want to know, is there a t value and an s value that if we put the s value in the second line and put the t value in the first line, we get the same ordered triples, the same x, the same y, and the same z. So what we do first of all is let's set the x's equal. Okay, let's set those equal. See if we can find a t and an s so that these two are equal. And let's do the y's as well. Okay, let's just see how this works out. Okay, so let me work through this, and I've got t minus 3s equals -8. And then down here I've got 2t minus s equals -1. Yeah, there we go. Now I just want to solve this. I guess the easiest thing to do is multiply this first equation by -2. So I get -2t plus 6s equals 16. And then down here I've got 2t minus s equals -1. And we get 5s equals 15, s equals 3. Ah, there we go. So s equals 3. Now I need to figure out, well, what is t then? So I just go back anywhere, like t minus 3s equals -8. If s is 3, I've got t minus 3 times 3 equals -8. And that means that t is equal to 1. So there, I've got this. I've got s is 3 and t is 1. Now, notice if I put those in here, like, okay, so if I put a t in for 1, so I've got x is equal to 1 plus 1, and down here I got s is equal to 3 times 3 minus 7. Both of those equal 2. Whoops, 2. So I've got an x coordinate of 2. Now let's find out what the y coordinate is. So we've got y is equal to 2 times 1 minus 5, just plugging in this. And also y is equal to 3 minus 6, which is -3 in both cases. So our second coordinate is -3. Now, here's the thing. The z's have to match and they have to be the same, or else there's no point of intersection. So let's see here. We've got z is equal to -3 plus 4, which is 1. And also z is equal to 3 minus 2. Oh, that's 1. Hot dog. There. Our point of intersection is 2, -3, 1. And that problem is done. Now we're down here to where we want to make some conversions. Okay, so we want to convert to polar form. We want to convert back and forth from polar to rectangular. Now remember the relationships here. We've got x squared plus y squared equals r squared. We move this over a little bit. Okay, we've also got x is equal to r cosine theta, y is equal to r sine theta, and tangent theta is equal to y over x. So these are the primary things that we keep in our knowledge pot as we go through and work these. Now, here we want to convert to polar form. Well, x squared plus y squared, heck, that's straight r squared. So this is r is equal to 6. X squared plus y squared equals 4x. Well, let's see here. This is r squared equals 4r cosine theta. Now, really, you normally don't want to just divide out the r the way I'm about to, but because you would, when you're solving an equation, like if I'm solving for r, I could lose a root that way. In fact, I would lose the situation where r is equal to 0. What I should do is bring the 4r cosine to the other side with r squared, factor and solve, using the zero product property. But just for this case, we'll say it's like I divide out the r and I get 4 cosine theta. Okay. This one here would be r squared equals 4r sine theta, or in other words, r is equal to 4 sine theta. Yeah, that's the way we do it. Okay, now we've got and those turn out to be nice because we're dealing with circles. Now we've got a line, and a line seems to be more natural to use rectangular coordinates, but I'm going to try to make it polar. So I've got 2r cosine theta plus 7r sine theta equals 1. Okay, and then I factor out the r and divide, and I get r is equal to 1 over 2 cosine theta plus 7 sine theta. Yeah, there we go. So you get something, 2x plus 7y equals 1. Didn't look bad, but this one looks ugly. Okay, now y equals 2. Well, that's just r sine theta equals 2. Divide by sine, and you get r is equal to 2 over sine, which is 2 cosecant. Same for here, you would do r cosine theta equals 2, or r is equal to 2 secant theta. Yeah, no worries there. Okay, now let's look at these. We're converting to rectangular form. Now, look, r equals 4. Man, I wish that were r squared, but it's not. It's r equals 4. And we know, so I can't just put it, I, I can't just put x squared plus y squared. However, you notice that I could square both sides. And if I square both sides, look what I get. I get r squared equals 16. Ah, now I can substitute in. So I got x squared plus y squared equals 16. And that's a circle of radius 4. This next one, we don't want to do that on this one. The previous one, we just squared both sides and it worked out nicely because we had x squared plus y squared equals 16. This one, we don't want to square both sides because we don't want a sine squared over there. We don't know what to do with that. However, I could multiply r, both sides by r. Yeah. Now look what I get. I get x squared plus y squared equals 4 r sine. That would be y. Yeah, that works out. Okay. Now, I don't know what happened here with part C. So I don't know what this business is about over here. But this one, we do the same thing. We have r squared equals 2r cosine theta. That means that x squared plus y squared equals 2x. Yeah, that's it. Okay, now we want to go to complex numbers. So we did the vectors, we did polar. Now we're on complex numbers. And we want to find the trig form. Okay. Now remember, here's what we need to do. We're going to need the modulus. Okay. It's like the magnitude, except now we got a different language here. This is the same as the magnitude. So we have 2 squared plus 3 squared. Okay, so this is the square root of 13. Okay, we want the now. So we have that, and we also can get the modulus of w, which is 5 squared plus 1 squared, square root of 26. So there we have the modulus of both of those. Okay. Now we're trying to find the trig form. So I need not only the modulus. Now remember, the trig form goes like this. Z is going to be the modulus of z times cosine of its angle. I'll say z like that, plus I sine of its angle. Okay. There's what the trig form looks like. And if so, now we've got the modulus, which is the square root of 13, but I need the angle. Now the angle is going to be the inverse tangent of the 3 over 2. See? It's the y over the x, the inverse tangent of the y over the x. Now that's true if you're in quadrant 1 or 4. But remember, if you're in quadrant 3, 2, or 3, that inverse tangent, you find the inverse tangent, but then you add 180 to it or add pi to it. Okay, so this is what we've got so far. And I want to round this to the nearest degree. And that comes out to be 56 degrees. Okay, rounding to the nearest degree. Okay, so as far as z goes, we've got z is equal to the square root of 13 cosine of 56 degrees plus I sine 56 degrees. There, that's z. Now we do exactly the same thing for w. Okay, w is equal to the square root of 26 cosine. Let me see what that is. Let me calculate that. We get 11 degrees, rounding to the nearest degree. 11 degrees. Okay, there we go. Yeah, that's it. That's it. Now, so if we're multiplying those two together, it would go like this. It would go the square root of 13 times the square root of 26 times cosine of 67 degrees. You add the two, 56 plus 11 plus I sine 67 degrees. Remember, we add those angles. We add them. 56 plus 11. Now, if we divide, we're going to take the square root of 13 divided by the square root of 26 times cosine. Now I'm going to subtract. So I take 56 minus 11. So that would be 45. Okay. 56 minus 11, that's 45. Okay. Okay. Now, if we want to raise it to the third power, I'm going to take the square root of 13 raised to the third power. Now, dig this. Here we go. Cosine of 3 times 56. Okay. Plus I sine 3 times 56. See? So we just multiply. That's it. Pretty simple. Okay. Just some. Now, when we talk about the root, okay, there's going to be 3 roots. So here we go. For this one, we're going to take the square root of 13 raised to the 1/3 power. And then we do this. We've got cosine. Okay, here we go. Cosine of the angle. What was the angle? 56 degrees. Okay, 56 plus 360K over N. Well, over, over N, which is 3. Okay. There we go, 3. Plus I sine 56 plus 360K over 3. And K goes from 0, 1, 2. See? So what we do is we're going to get these 3 roots. And we first of all, here's the first root. Here's when K is equal to 0. What we get is 13 to the, well, let's do this. We've got the square root of 13 to the 1/3 power, okay? And then we've got this. We've got cosine of 56 over 3 plus I sine 56 over 3. Now, K equals 1. Well, that one's going to be the square root of 13 to the 1/3. And then cosine of 56 plus 360 over 3 plus I sine 56 plus 360 over 3. And you could use radians. Then we've got K is equal to 2. And of course, you'd work these out, but then you've got the square root of 13 to the 1/3 cosine of 56 plus, what is it, 720 over 3 plus I sine 56 plus 720 over 3. And, you would work those out and you would get your 3 roots. Okay, now, jumping over to the parametric form of the conics. First of all, if you've got a circle, you've got the counterclockwise parameterization. You've got x is equal to r cosine t plus h, y equals r sine t plus k. Now, if you go the other way, just switch those. X is equal to r sine t plus h, y is equal to r cosine t plus h plus k. Sorry, plus k. Yeah, there it goes. So that's the way you deal with the circle. Now, if you have an ellipse, so let's suppose we have x minus h squared over a squared plus y minus k squared over b squared equals 1. Okay? Counterclockwise, x is equal to a cosine t plus h. Y is equal to b sine t plus k. Clockwise, x is equal to a sine t plus h. Y is equal to b cosine t plus k. Yeah, that's it. So if you go up and look at these ones, this is x is equal to 2 cosine t, y is equal to 2 sine t. Now that's going counterclockwise. Clockwise would be x is equal to 2 sine t, y is equal to 2 cosine t. Yeah, no worries. No worries. Now the next one, well, we just, pretty much the same. We've got 2 No, 4 this time. Okay, we've got 4 cosine t plus 2, and y is equal to 4 sine t plus 2. Actually, not plus 2. What am I doing? Minus 5. Sorry about that. Minus 5. Sorry. Sorry about that. Minus 5. Yeah. And down here, going the other way, you get x is equal to 4 sine t plus 2, and y is equal to 4 cosine t plus minus 5, minus 5. I'm stumbling here. Okay, so I got to be sure. Okay, yeah, there we go. That's it. Okay, now for the ellipse, here we've got 2. So here we go. X is equal to 2 cosine t plus 2, and y is equal to 5 sine t minus 5. Yeah, like that. And down here, this one would be x is equal to 2 sine t plus 2, and y is equal to 5 cosine t minus 5. Yeah, okay, just make sure I got those right. Okay, there we go. Now I think that's it. I think that's everything. So good. Hey, look, I rushed through this fast. It was very quick. So don't hesitate to ask questions if you have them.